Now, I am going to introduce the background of ammonia. Ammonia is one of the most highly produced inorganic chemicals. The chemical formula is NH3. It is colorless gas with pungent smell, and it produced naturally in human body and nature. However, it is toxic to human cells. Therefore, it is converted to urea and eliminated through human urine. History of ammonia. Formerly, ammonia obtained by the dry distillation of nitrogenous vegetable and animal product, by the reduction of nitrous acid and nitrate with hydrogen. Today, most ammonia is produced on a large scale by the Haber process with capacities of up to 3,300 tons per day. In this process, nitrogen and hydrogen gas are allowed to react at a pressure of 200 bars. Usually, ammonia was used in fertilizer and household cleaning products. Besides this, it can be used as manufacture of other chemicals such as textile, explosive, plastic, and pesticide. The harmful effects of ammonia are inhalation, skin or eyes contact, and ingestion. For inhalation, exposure to high concentration of ammonia in air causes immediate burning of the nose, throat, and respiratory tract. This can cause broncholar and alveolar edema and airway destruction, resulting in respiratory distress or failure. Inhalation of lower concentration can cause scorching, nose, and throat irritation. For skin or eyes contact, exposure to low concentrations of ammonia in air or solution may produce rapid skin or eyes irritation, while higher concentration of ammonia may cause severe injury and burns. Lastly, shallowing of high concentration of ammonia solution results in corrosive damage to the mouth, throat, and stomach. Ingestion of ammonia does not normally result in systematic poisoning.
In a modern ammonia producing plant, the process including sulfur removal, steam reforming, ammonia conversion, shift conversion, carbon dioxide removal, methanation, and ammonia synthesis too. At the early stage of the process, natural gas such as methane was used for conversion of hydrogen gas. Before the conversion, the compressed and heated natural gas was fed into the hydrogenation reactor for converting the organic sulfur compound in the feed into hydrogen sulfide gas. The hydrogen sulfide gas was then absorbed and removed by the absorber column. The sulfur-free natural gas was then fed to the tube furnace with the injection of steam. In the tube furnace, the methane gas was undergoing steam reforming to produce hydrogen gases and carbon monoxide. From the tube furnace, the gases were fed into ammonia converter with the presence of air. In the converter, the hydrogen gas was catalytically reacted with nitrogen to form ammonia. The output stream of the converter was connected to CO converters, which used to convert carbon monoxide into carbon dioxide by using steam. As we can see, the steam boilers were built as connected to the converter, which used to boil the water into the steam. In the carbon dioxide absorber, aqueous monoethanolamide solution was fed to absorb carbon dioxide gas in the gas stream. The bottom flow monoethanolamide solution will be recycled back for regeneration. The regenerated aqueous monoethanolamide will then fed to the absorber inlet. The gases came out from the carbon dioxide absorber contain large composition of ammonia gas, while small amount of carbon monoxide and carbon dioxide were still left in the stream. For completely remove the residual carbon monoxide and carbon dioxide, hydrogenation vessels was used. Both carbon monoxide and dioxide were reduced to form methane gas and water. The makeup gas was then compressed and cooled before sent to the condensation column. In the condensation column, a cold gas was injected to condense the ammonia gas into liquid. The effluent gases from the column was sent to a heat exchanger and preheater to preheat the converter feed gas. The ammonia converter is a high conversion purpose with high temperature. The high temperature outstream was fed into a heater, which used to heat up the water for heat exchanger. The effluent was then cooled down and passed through a separator to separate liquid ammonia and purge gas.
One of the major equipment that we have chosen to analyze is the hydrogenation reactor in the ammonia plant, and is one of the preliminary processes that the natural gas have to go through before it is further processed to become ammonia. In the hydrogenation reactor, natural gas is passed through it to have the sulfur element inside it be removed in order for the gas to not contaminate and deactivate the catalyst that will be used in the subsequent processing steps, as the catalyst that will be used later on is quite sensitive to the sulfur element. The reaction that will be happening in the reactor is as shown in the slide, where hydrogen gas and natural gas will react to form hydrogen sulfide, thus removing the sulfur from the natural gas. The reactor that is normally used will be a catalytic fixed bed reactor, where the reactants will flow through a fixed bed reactor packed with catalyst to trigger the sulfur hydrogenation reaction. The catalysts normally used are alumina-based catalysts impregnated with molybdenum and cobalt or nickel. As seen in this slide, the image displayed is the conventional control process for the hydrogenation reactor. In the image, the hydrogen gas is controlled by a mass flow controller before being fed into the reactor, while the pressure inside the reactor is controlled by a type of valve named the dome-loaded back pressure regulator with a set point. After some analysis, the objective of this conventional system is the control of the pressure in the reactor in order to maintain the conditions for the reaction to take place, and also for the optimum rate of reaction, which is at a pressure and temperature of 30 to 130 atmospheric pressure and 300 to 400 degrees Celsius. The disturbance variable is found to be the flow rate of natural gas, while the manipulated and controlled variable are the mass flow rate of the hydrogen gas and the pressure of the reactor. For the proposed control system, it is proposed that a ratio station be added in combination with flow controllers and valve to control the ratio of the hydrogen feed and the natural gas feed, while a fired heater is added before the reactor with a temperature controller to control the temperature of the feed into the reactor, while a pressure controller is attached to the reactor to control the pressure inside the reactor. In this case, feedback control is used as it is much cheaper, as well as the range of temperature and pressure being quite big enough to allow for offsets. The advantages of using a ratio station is the ability to maintain the stoichiometric ratio of hydrogen gas to natural gas to reduce formation of byproducts and reduce wastage of hydrogen gas, as it is very expensive. Next, the advantage of the fired heater is that it is able to heat up and vaporize the feed to desired temperature and maintain it. Lastly, in the reactor, the pressure control will be able to maintain the pressure of the reactor to prevent overpressure and to achieve optimum rate of reaction.
The second major equipment is the CO converter, which consists of two adiabatic fixed bed reactors, the high temperature and low temperature shift conversion reactor. In high temperature, processed gas passes through catalyst at 350 to 380 degrees Celsius. The high temperature favors fast reaction rates but is thermodynamically limiting. The gas exiting the high temperature process is then cooled and passes to the low temperature process. In the low temperature process, gas passes through catalyst at 200 to 220 degrees Celsius, where more carbon monoxide is converted as the reaction is thermodynamically favored by the low temperature. The objective of the process is to maximize the conversion of reactor, but temperature limit should not be exceeded. One way of meeting the objective is controlling the temperature. Temperature affects the conversion as it affects the thermodynamic and kinetic rates in the two reactors. Secondly, temperatures that are too high will cause deactivation of the catalyst. For temperature control, the control variable is the reactor temperature. Since the reactor is adiabatic and the reaction is exothermic, the temperature will increase down the length of the reactor. The temperature can be measured by measuring the temperature at several points down the length of the reactor. The second control variable is the feed inlet temperature. In high temperature conversion, the feed needs to be heated before entering the reactor, while in low temperature conversion, the feed needs to be cooled as it enters the reactor. Manipulated variable is the heating fluid flow rate, and the disturbance variable is the inlet composition of process gas. The proposed control is cascade control. The block diagram of cascade control is shown above. The schematic of the high temperature converter is shown. The reactor temperature control is the master loop, while the feed temperature control is the slave. For the master loop, the control variable is the reactor temperature, and the master controller uses its measured value to establish the set point of the slave loop. The feed inlet temperature controller in turn adjusts the flow rate of the heating fluid. The process is same for low temperature conversion, except the manipulated variable is the cooling fluid flow rate. Conventional feedback does not have a slave loop. Its response would therefore be slower, as when there is a disturbance in feed temperature, the reactor temperature would have to deviate from set point before corrective action is taken. The dynamics of the inner loop is much faster than the dynamics of the outer loop, so cascade can be used in this case. The advantage of cascade control is improved performance because of faster response before system deviates from set point. Another advantage is that it acts on disturbances that are from the manipulated variable.
So the next equipment that we are analyzing is the carbon dioxide removal process in the ammonia plant. The flue gas from the converters is mixed with the amine solution, water, and the solution coming from the lean exchanger. The absorber outlet is then processed in the lean exchanger to get lean solution, which goes into the stripper to get the condensate and the carbon dioxide with the condenser and reboiler. For the optimization, the objective function will be the total equivalent work, which is the energy per kg of removed carbon dioxide. To reduce the operating cost, which is mainly from the heat for the reboiler of stripper and the electricity of water pumps, the heat need to be converted into equivalent thermodynamic work. So the first constraint will be the environmental requirement, which is to capture 90% of carbon dioxide. The next will be the temperature of the lean solution to the absorber, which is ideal for the absorber to keep it around 50 degrees Celsius. Other than that, the pressure of the stripper top pressure needs to be controlled below 2 bar to prevent the degradation of MEA solution. For the disturbance variables, the constraint discussed previously will be part of it. However, small variations of carbon dioxide recovery and 10 degrees Celsius difference of the lean solution temperature may not affect the objective function too much. Therefore, the main disturbances will be the composition and flow rate of the inlet flue gas and the pressure of the stripper top. For the proposed control system, 9 valves are used, which also indicates 9 degrees of freedoms. 4 controllers are used for the level control, 2 in the stripper, 1 in the absorber, and 1 in the surge tank, which are valve 1, 2, 6, and 7. The control variables of these valves are the levels of the fluid, and the manipulated variables are the outlet flow rates from the respective equipments to prevent fluid overflow. The third valve is controlling the pressure of the condenser, and the manipulated variables is the outlet flow rate of the carbon dioxide. This controller is used to keep the pressure low in the condenser. The fourth and ninth valve have the same control variable, which is the temperature of the fluid, and the manipulated variable is the cooling water inlet flow rate. These controls are used to control the temperature at ideal conditions. For the fifth valve, the manipulated variable is the reboiler duty due to the slim inlet flow rate, and the control variable is the temperature of the fourth tree in the stripper. Temperature control at lower tree in the stripper is easier and faster as compared to concentration control to optimize the performance of the stripper. The 8th valve is used to control the concentration of the solution coming out from the absorber. The manipulated variable is the outlet flow rate from the surge tank. This is to control the concentration of the solution at ideal conditions.